Hello, so I want to just go through how pain works because it's really not that painful of a topic. If you're new to the channel, which you should be, this is the first time I've ever made anything on here. I'm basically just going to go through on MS Paint like a map of exactly what happens and break it down for you. So the first thing I really want to get out of the way is the very basics because at the end of the day, if you've got something, you can simplify it down and make it more basic. So essentially, for pain, what you've got is you've got this nociceptor here, which is just a type of receptor, which is specifically designed to detect pain. And then you're going to have a little neuron coming out of that, going into the sort of main spinal area. So let me just draw on a little synapse. And that's essentially everything that's happening in your peripheral nervous system. So if I just draw a little box here, and then what you're going to have over here coming out of this guy is going to be another neuron, this time in the spine, and this is going to be called the dorsal horn neuron, which essentially takes our transmission saying hello, this hurts, all the way up to the brain, which is where you're going to figure out what hurts, why it hurts, how much it hurts, what you've done, what you need to do, all of that fun stuff. So here we have the spinal tract, and then here we have the brain, the big smarts figuring everything out. And in essence, that is what we're dealing with. This is the framework which everything else is going to be built off of. Ignore the very wonky lines. It isn't supposed to be a very professional looking diagram. But these are sort of the three main things we need to focus on, really. And that is, in essence, neurons. But let's fixate down first and focus on the nociceptor here, which is this blob as I've represented it. Let me drag this down a little bit so we've got a bit more space. So you kind of have to start out by thinking, what is pain ultimately? What are you actually detecting when you're detecting pain? Because we have a pretty good idea of what pain is, but to a cell, we need to be able to define it or register it somehow, and that's where the nociceptor comes in. And generally, what happens when you've got something that hurts is your cells are somewhat damaged. So we've got a damaged cell here. It's had a bit of an issue. Something's gone horribly, horribly wrong. So this cell here, this green cell, could be any cell anywhere in the body, really. That's the point of pain. Has burst. It's seen the end of its life, and it's burst. And essentially, what's happening now is a bunch of things that aren't supposed to be outside the cell, like potassium ions, things like ATP. You'd never see ATP outside of the cells unless something has gone horribly wrong, and protons as well. Protons you won't see outside of the cell unless you have some sort of major system issue. These are all things which can actually be physically detected, and this is actually what's going to tell the nociceptor something is not right here. But the the nociceptor still needs a way to detect that this has happened, and so like many sort of neuron-related structures, the nociceptor has a equilibrium potential across its membrane. It's constantly at resting potential unless it detects one of these three things. Now, potassium is just potassium. Uh, it's going to depolarize the membrane just by existing because potassium typically is supposed to be inside the cell. That's how cell potentials work. So if you've got extra positive charge outside of the cell, that is going to cause depolarization right off the bat. Potassium has depolarized the cells. The more potassium you've got leaking out of your cells, the closer your nociceptor is going to be to having some sort of action potential, which will stimulate this nociceptive neuron, which we'll get to in a minute. ATP is a little bit different. So with ATP, you have these ion channels on the cell surface, which are sodium channels. That's a very big sodium channel, but you get the idea. Let's draw some sodium going in. Sodium channels, and essentially they will open in the presence of ATP. Sodium channel opens, sodium flows into the cell, depolarizing the membrane more, bringing it closer to that threshold potential. Hydrogen ions act in almost exactly the same way. You can have acid sensing ion channels. So this is the ATP here acting on the sodium channel. You can have hydrogen atoms acting. Oh, that's a funky looking curve. Acting on the sodium channel there. But the acid can also do other things as well. It can activate these specialized sodium channels. You've got specialized sodium channels called trip channels. There we go. And trip channels are activated by a number of different things. So one of them is hydrogen ions, so protons being released from these ruptured cells. But they can also be activated by other things as well. So let me just pop that here. So the trip channels, which you know is VR1 channels, I'm going to call them that just because it's easier to write. They can also be activated though by heat. So all of these things, which could be associated with pain, activate the TRIP or VR1 sodium channels, alongside these things being released from the cells. So all of these things are working to depolarize your nociceptor here with the aim of trying to generate an action potential, which will go on to alert the rest of the system here that pain is existing and you probably need to do something about it, whether that's put pressure on a wound, whether that's move away from a hot object, whatever pain is. But often this isn't quite enough because ultimately, this response could be quite small, but you kind of need something that's going to exaggerate that pain because ultimately you can feel pain, but then afterwards you need to be incentivized to do something about it. And that is where sensitization comes in. Sensitization essentially makes these receptors here, I forgot as well, there's a mechanoreceptors will also work here as well, like really intense pressure will also stimulate sodium channels. But you need something that's going to make these receptors here continually active even after that stimulus is gone, to make you, the organism, aware that you need to do something about this wound or this gash or whatever's happened to you. You need to do something about it even after the initial cell damage has been done. And that is where sensitization comes in. These receptors will suddenly become a lot more sensitive to anything, and that involves a very important substance called substance P, which essentially is released from the nociceptors when they are stimulated by this influx of sodium. Well, these lines do not like me today. So substance P will actually act on the blood vessels out here. So let me just zoom out a little bit here. Oh, that's a horrible looking blood vessel. Let's make it red because blood is red. It's the obvious color to make our little blood vessel here. This is a blood vessel. It doesn't look very much like a blood vessel, but it is a blood vessel going on about its business down here. But substance P is going to go into this blood vessel here, and it's going to, the technical term is make it leaky. But what that actually means is that this blood vessel is going to start releasing protons, ATP, and potassium ions, all with the effect, obviously, of causing more of all of this that we've just discussed here, causing more sodium to go into the nociceptor, raising the action potential further and further towards that threshold that it needs to exceed to actually generate an action potential. So essentially, this is a bit like a positive feedback loop, because as soon as you get this substance P coming out, you're pretty much guaranteed to get an action potential. But this also has a secondary sort of thing that it causes, and that is inflammation, because obviously you're essentially breaking down parts of the walls of the blood vessel to let things out. You're going to get these immune cells which are just chilling in the blood vessel, and they're going to be like, whoa, this is damage, we need to do something about this. This is going to cause an inflammatory response. And I'm not going to go into the whole mechanism of inflammation here, but it is worth noting that it produces some important players in this game. So the first of these players we need to talk about is something called nerve growth factor, or NGF, and this simply acts on the receptor here to cause it to decrease the threshold for excitation. A fairly simple interaction. I'm not going to go into the ins and outs of it. But a more sort of specific response comes when you have things like bradykinin and histamine. These will directly affect the trip channels up here, the ones that responded to heat and acid. That will directly act on those, increasing their opening. And it will do this through the power of G protein coupled receptors. So how shall I draw a G protein coupled receptor? Let's do it like a little box. There, this is my G protein coupled receptor right here. And that is going to act on the trip channels, which I'm just going to draw another trip channel here because I don't really fancy drawing an arrow all the way over there. That's just going to get messy. So we'll just draw another trip channel here, like so. And again, that's going to allow more sodium to come into the cell, depolarizing the membrane, bringing us closer to that action potential. So you've got loads and loads and loads of ways to bring about that action potential. That is a fat arrow. That is way bigger than all the other ones, but it's not supposed to be bigger. It's just fat. That's all. There we go. We've got a fat arrow worth of sodium coming in. And then the final one we need to think about, I realize I've drawn this very badly now, is prostaglandin. Okay, so now I've just moved this over here, so I've actually got space to do the prostaglandins section. I also made the fat sodium the same size as the other trip channel over here, so it's a bit more obvious it's the same thing. But don't worry, I made up for it by making a mega fat arrow from inflammation to prostaglandins, nerve growth factor, and bradykinin histamine, so we're all good. Anyway, the prostaglandins also act on a G protein coupled receptor, like this one, and what that does is act on the bradykinin G protein coupled receptor to open the sodium trip channels. So basically, they're too lazy to act directly on it themselves. They have to act through an intermediary, which I think, a bit lazy. They could pull their weight a little more and act directly on the sodium channels, but they act on it through this GPCR here. And that is essentially peripheral sensitization in a nutshell. There's other processes that go on. This is sort of the surface level stuff that I'm aware of. But this is all with the goal of raising the membrane potential of this nociceptor. So you're more likely to get action potential, and you're going to get more action potentials to go down this neuron here. And that is where we are going to focus next. This little tiny, very thin neuron. There's multiple different types. The main two types of this neuron are we have C fibers, which generally tend to deal with slower, more gradual pain. Say I was slowly pushing down on your skin and it was, hurting over time. That's the sort of thing that they deal with, and they are generally have a slower response because they are less myelinated. Wow, I cannot spell at all. Gradual. That's my typing, not my spelling, trust me. Yeah, so they generally are sort of the slow, sustained pain. Whereas what you also get is you get delta fibers. I don't think I have a delta on this keyboard. They're called A delta fibers. I guess I'm only going to be able to call them A fibers because there's no delta here, but there should be a delta after the A. They deal with like rapid, fast pain. Say you just scraped your knee and it suddenly stings, it hurts. That's the sort of thing they deal with. They are generally slightly more myelinated, but not like hugely myelinated. And they're still slower than like your regular sensory neurons, but they are faster than C fibers, and you will feel that a lot more. I will find a delta to put in there in the next clip. But those are sort of your two types, essentially. And they both have this at the end, and they both have this afterwards. But it's just worth knowing there are two different types, and they will deal with two different types of pain, because pain isn't really necessarily always one thing. But then you get to this next synapse here. And this is another synapse, and another synapse is another opportunity to amplify the pain. When in doubt, these pains will always amplify as much as possible because you want to hurt as much as possible, because doesn't pain feel good? Here we get something called central sensitization. So how exactly does this central sensitization, as opposed to your peripheral sensitization, actually occur? Well, if you guessed, it was more substance P. Congratulations, substance P does make a grand return. And also sometimes something called calcitonin gene-related peptide. But that's less important here. Mostly we're worrying about substance P, which is being, again, released from the ends of these A and C delta fibers. Also being released from the ends of these A and C delta fibers is our first neurotransmitter of the day, glutamate, going across this little synapse here. Obviously, this is a excitatory synapse in the central nervous system, so we can have glutamate as our neurotransmitter. It's going to be doing its usual glutamate thing. It's going to be acting on its AMPA and NMDA receptors, exciting this neuron and causing an action potential. But of course, as we know with sensitization, simply just passing on the message, simply just having a little bit is not enough. We need sensitization to not only cause this neuron to be stimulated, but also cause it to be continually stimulated, even if some of the stuff down here stops stimulating, which is where substance P comes in. I now realize I've left myself very little room on this neuron here to draw any room. Let me make this a little bigger real quick. Okay, I've just made this go super fat. You can kind of see weird bits, but I'll get rid of that later. Anyway, substance P is going to come in here, and it's going to act on another G protein coupled receptor up on the membrane up here. So now I've got space to actually pop this in. It's brilliant. This is called a neurokinin 1 receptor. There we go. It looks beautiful now. Anyway, this is called a neurokinin 1 receptor, or NK1, because as with all scientists, I like to abbreviate my letters so I don't have to write out loads of different things. And this is a GQ protein. So that means it's going to have an excitatory effect on this membrane system here, which is what we want if we want to increase the amount of action potentials we're getting out of this system. So the things it's going to act on are basically going to be all of our ion channel friends. So let's just draw all of our ion channels. So this is going to be our potassium ion channel here, with our potassium, just trying to get out. But you know what? Neurokinin 1, once activated, is not going to let him. There is going to be no potassium coming out of this ion channel. These guys are going to be shut down by the neurokinin. You know what isn't going to be shut down by the neurokinin? Are sodium and calcium channels. Obviously, the sodium going in and the calcium going in are going to depolarize the membrane more. So we're going to get more action potentials. It's also a GQ protein coupled receptor, which means we are just generally going to get an increase in calcium levels. It's going to release calcium from the endoplasmic reticulum. So now your dorsal horn neuron is all stimulated. It's got loads and loads of inputs coming into it constantly. It's got sensitization at the central level, it's got sensitization at the peripheral level, and it's got these inputs from the actual source of pain itself. It's going to be passed on into the brain, and the first structure it's going to encounter here is the thalamus, and the thalamus is going to be a good boy and pass up that information to the other brain centers, which need to be aware of the fact that you are being hurt, essentially. So the thalamus is going to pass its information on to the somatosensory cortex. Have I spelt? No, I've messed that up. Somatosensory. I can't type and speak at the same time. It's a problem. And the somatosensory cortex is going to be doing all of the actual legwork in making you feel really crap about the fact that you are hurt. It's going to make you oh my god, oh, I'm hurt, ow, ow, ow. That's that whole sort of mindset and mood aspect of it that comes from the somatosensory cortex. So it's going to lower mood, And it's essentially going to make you pay attention. It's the whole sort of psychological side of why, ow, I need to do something about this. And that is essentially, in essence, the whole entirety of why it hurts. But the thing is, it doesn't keep hurting forever. Because if it did keep hurting forever, you just have these positive feedback loops going round and round and round, and the pain would just never stop. And so this is essentially where opiates come into the picture. Not the drugs that people sometimes take recreationally, and the British tried to get the Chinese hooked on a war once, multiple times, sorry, but instead the neurotransmitters in your body, which stop the pain. Which is a good thing after a while. You don't want it to hurt forever. So essentially, the somatosensory cortex is very smart, and eventually it figures out through other neuronal inputs that there's not much of an issue anymore, and this whole system can kind of wind down a little bit and stop making such a big fuss about all of this pain nonsense and man up a little bit. So it sends a signal to a region called the preaqueductal gray. I'm pretty sure I'm pronouncing that right. I never know if I'm pronouncing these words right because I don't know who came up with them, but they really did come up with some of the most complicated words they could possibly imagine when they named the brain regions. I'm going to call it the PAG because it's nice and simple. And essentially, the PAG is stimulated by the somatosensory cortex. It's going to give the PAG a little bit of glutamate and say, yo, go stop all this pain. But there is a sneaky extra step, unfortunately, because there is this bonus neuron here, this inhibitory neuron, which is off to the side here. Let's see, it's going to be, this is a nasty neuron because it's inhibitory, so we're going to make it red. Hopefully that's not going to be too confusing with the blood vessels. I'm sure you'll be able to figure out. This one's an arrow. This is inhibiting the PAG with GABA, which is the main inhibitory neurotransmitter in the central nervous system. It's sending its GABA signals into the PAG saying, actually, you know what? Let's keep the pain going a little bit. So you kind of need to be able to balance between these two things, essentially. And the real sneaky part about this little GABA neuron here is actually it's all being puppeteered by the same system. The somatosensory cortex is puppeteering this GABA neuron and is the one saying, actually, let's keep it going. So at the end of the day, it's up to the somatosensory cortex to tell itself to stop inhibiting the PAG and start stimulating the PAG. But unfortunately for the somatosensory cortex, it just starts blasting glutamate out this system. It's not going to stop this guy here, the little inhibitory neuron. Even if it stops putting glutamate down this guy, this little inhibitor guy is still going to be very much active. What the somatosensory cortex actually has to do is inhibit both of these neurons here. And so how does it do this? Let me draw it in a curly arrow's eyes. We're not going to be able to see what's going on. This is where the opiates come in. Specifically the opiates used, and again, I can never spell these, so please bear with. Acanthalins and endorphins here. These are opiates, essentially, and their sole purpose is to shut down this whole system here so that the glutamate stimulating the PAG can actually stimulate the PAG to stop all of this nonsense which we discussed down here. So it seems like a very convoluted system, but that's the way our body does it, and it's that complexity which allows us such fine control over these systems, essentially. So this guy here inhibits. I should really draw them in red because they do inhibit, because they are inhibiting these. Let me change that real quick. You didn't see anything. These guys aren't orange. These guys are little inhibitory boys. Once the PAG is finally free to stimulate, it's like, thank God, finally I can actually do something useful. I've been sitting here, not part of this system for ages. You've just been winding up and winding up and winding up all your positive feedback loops. And so it is now going to send off a signal to the Raphe nuclei, and specifically the Raphe nuclei magnus, which sounds very ominous, but again, I wasn't the one who named all these structures. I'd like to have a word with the guy who named all these structures, really, because I can't spell or even think of. Most of them, they're too complicated. And this is the opiate boy. This is the guy who's actually going to be dealing with all of this crap which we created up here, and is going to be sorting everything out for us. So the first thing the raphe nuclei are going to do is send out a big old arrow here to this synapse, which, if you remember, is between the dorsal horn neuron here, which is our whole wind-up neuron, and the neuron which feeds into the thalamus and just tells us that everything hurts. And this is going to be inhibiting transmission at that synapse. And once again, this is going to be our enkephalins and endorphins. I'm going to copy and paste because I don't have to spell them out again. But I mean, there's still quite a lot that needs to be inhibited. We have ranked up a lot of stimulation from all of this feedback stuff back here. There's still a lot going on, so we still need to inhibit more. We've stimulated a lot. We need to inhibit a lot now as well. And so what is the best way to stop the pain on a wound? Well, usually it is to apply some pressure. And that is exactly what we are going to do here. Let's use a different, let's just use an arrow for this one. Probably makes more sense. So we've not yet discussed the effects of just sort of general sensory input, which is different from pain input. But we can, by applying pressure or mechanoceptive force, decrease the amount of pain. And that's just through your normal pressure receptors. They will feed in into this central sensitization here and inhibit this synapse, decreasing a little bit more of our sensitization. But there is another way that our raphe nucleus magnus can also help us out down at our central sensitization as well. So let's actually give the raphe nucleus magnus another little branch coming out here. This time another inhibitory neuron. I'm going to do the inhibitory neurons in red. I've decided I'm just going to give them a purple innard so they don't look like blood vessels. That was my big worry. I did not want to do like blood vessels. And this is another opiate neuron, which is going to go over and deal with our synapse over here. And in this synapse here, I believe it's serotonin, which I'm just going to call 5-HT because, again, shorthand, nice and easy. And I think, is it acetylcholine? No, it's noradrenaline. In this synapse. There we go, they're vibing. I should have really left more room actually as well, because you can also get inputs in here. I'm just going to draw it here. You can sort of see. We're also going to get a little bit extra help from some other brain regions as well. They're going to join in the party because they're kind of sick of all of this whole pain stuff now. It's just gone too far. It's hurt for too long. We've sorted it out. We've gone to the doctor. They fixed us up. So the locus, what's it called? I can't spell. Why can't I spell it? Locus coeruleus. Again, I'm not great on the pronunciations. I apologize. It's also going to join in the inhibition party, and they are also going to stimulate this receptor here, which is going all the way over to our central sensitization synapse, going between our A delta and C fibers and our dorsal horn neuron. And this is simply going to inhibit. So it's actually going to act on both the pre and post-synaptic ends. Oh, that line did not come out how I expected. It's going to act on both the pre and post-synaptic ends of this synapse here. So we're going to have an enkephalin inhibitor here and an enkephalin inhibitor here. So on the post-synaptic membrane, it is going to come back to our favorite friends, the potassium ion channels, sorry. And finally, these guys, if you remember from before, were getting inhibited up here by our neurokinin 1. And now the enkephalin is going to come in here and be like, actually, you know what? Potassium leaving this membrane is actually kind of cool. We actually kind of want that now. So let's open up some more potassium ion channels. Let more potassium out. Let the membrane repolarize or hyperpolarize back to its original resting state. Very cool. If we were to come over to the presynaptic node over here, again we're going to get iron enkephalin going across the membrane, and what it's going to do this time is it's going to see these little calcium channels here, just chilling, and it's going to be like, you know what, you guys, you should really chill out a little bit, take a day off work, stop pumping quite so much calcium into this presynaptic node, because you're really causing a lot of neurotransmitter to be released here. So you know what? Let's just cancel you guys. So that is how it is supposed to work, like all the time. But unfortunately, we humans have a little thing about pain. We don't like it very much, and we like to try and get around it, whether that's because we just don't like pain or because we have an actual medical condition which is exaggerating the system or making this whole process not work as it's supposed to. But there are two main classes of drugs which can act on this system. Those are opiates. Yes, those are the ones that the British got the Chinese hooked on to try and invade China, and on non-steroidal anti-inflammatory drugs. So let's start with the non-steroidal anti-inflammatories, just because I think they act as a nice starting point, because they bring us right back to the start here, to our peripheral sensitization, the process which started this whole cascade, and we need to talk about them. So anti-inflammatory drugs, they're somewhat self-explanatory, because down here we have a little something going on called inflammation. And as the name might imply, anti-inflammatory drugs prevent this inflammation, and hence the membrane potential will hopefully never get high enough to send enough signals to the brain that you're going to have any sort of significant amount of pain. So the way they actually target inflammation is in the production of these prostaglandins here. So the prostaglandins aren't just produced by inflammation. There's actually a couple of steps, but the main step we need to kind of think about when dealing with these drugs is how they are made from their precursor and their precursor's precursor. So it's mostly this conversion from this acid, which I can't pronounce because I'm bad at pronouncing words. We've got established that already, and the prostaglandin H2. So what actually happens in this synthesis process of prostaglandin is there is an enzyme called COX, which is responsible for this conversion. I'm going to put it in blue, then you know it's an enzyme. So what these non-steroidal anti-inflammatory drugs, or how do you even say that? NSAIDs? I don't know. Anyway, what they do is they are going to inhibit COX, and that can work really well in some circumstances, but it can also carry a certain degree of side effects. You see, COX is not exclusive to the prostaglandin synthesis process. So you can get COX1 and COX2. COX2, it's not very widespread. It's kind of fairly restrained to the synthesis of things like prostaglandin, whereas COX1, no, COX1 is not restrained to that sort of thing, and so with COX1 being inhibited, you can get effects like gastric irritation and potentially kidney problems. But I mean, overall, a lot of very safe drugs are non-steroidal anti-inflammatory drugs. A lot of very safe painkillers are, and most of them act at this COX enzyme. So for the next group of drugs, we're going to come back over to our friend the PAG and RAFA nucleus over here, and these are essentially opiates. Now, opiates essentially mimic these endogenous opioid neurotransmitters here, so endorphins, enkephalins. They can act on a variety of different receptors, because these guys actually have lots of different receptors. They tend to act on the mu receptors rather than the kappa and the delta receptors, because the mu receptors are found everywhere. Kappa and delta receptors are less widespread, they're more limited. So you'll generally find them acting on these sorts of pathways here. And essentially, they just act as agonists on these receptors here, enhancing this pathway and preventing pain much earlier and much more successfully than your body would allow for. And so essentially, those are the main ways that you can prevent pain or decrease at least the sensation of pain. There are a couple of other smaller, lesser used drugs, and it basically just involves blocking a bunch of receptors. So you can block these bradykinin receptors here. If you put a receptor blocker in, you're reducing your peripheral sensitization. You can block your neurokinin 1 receptor up here, which will prevent your central sensitization, and you can block glutamate receptors, NMDA and AMPA receptors here. Obviously, you do need to be a bit more specific. If you're doing something like glutamate, it's a lot more specific, a lot less specific, sorry, to the pain reception pathway. There is also some success with selective serotonin reuptake inhibitors and cannabid agonists, though I'm not 100% sure on their actual mechanism of functioning. But in essence, that is everything that I know and think is worth sharing about the pain pathway and how it operates. If you found this really useful, please let me know. I've never really done anything like this before. I have no idea how useful this will be to anyone, but please do let me know. And very importantly, please, if I've made any mistakes in this, please do point them out to me. This is only based off of my understanding of the subject. I do not claim to be an expert in this subject. This video is as much for my own education as it is for everybody else's. So please, if you doubt anything that I say for any reason, please do second guess it and second source it. I'm not the utmost source of authority on this topic. But thank you very much for watching, and if you would leave a like and a comment, that would be very much appreciated. And I will see you hopefully in another one.